Okay, so yeah, thanks everyone for coming. I'm happy to have a chance to talk about the topic I'm interested in today. There's some nice work we've done with Devere and Nathan. So we're going to talk about quantum simulation of Lindbladian dynamics via this method called repeated interactions. So I'll just give an overview of what I'm going to cover in the talk. I'll briefly introduce Hamiltonian simulation, but I don't have to spend too much time there because Sophia did a great job already talking about that. Then I'm going to motivate the non-unitary or Lindbladian simulation, which we're interested here. And then I'm going to introduce this approximate correspondence between these Lindblad equations and what is known as repeated interactions, or CPTPs, so completely positive and trace-preserving maps, which are just required to preserve the notion of our density matrix or the validity of it. And then our goal is to use these repeated interaction maps to form some sort of iterative unitary process that can produce the Lindbladian dynamics, and then implement those maps on the quantum computer. And as Sophia also nicely highlighted, quantum computing is very natural to implement unitaries, but not always very clear on how to go about doing non-unitary processes. And I've also included the archive link below if you're interested. All right, so just briefly, quantum simulation. That's fun. So we all know from quantum mechanics that states are evolved by a unitary propagator, and in the talk, all operators you can write down are going to be time independent. And then the goal of simulation is to find an algorithm that constructs some unitary, so we can get an epsilon close approximation to this propagator in the case of simulating Hamiltonians. And then I don't need to motivate this much, as we just heard previously, but we can study the time evolution of observables, or learn the eigenvalues of large classically intractable Hamiltonians, for example, those of large molecules in chemistry. And then the algorithmic question is, how do we efficiently build U? And I'll just quickly discuss some state-of-the-art complexity to give context to the results later in the talk. The algorithms also, Sophia mentioned, qubitization or the quantum singular value transformation gives the following state-of-the-art complexity, which is linear in time, and this alpha is called a coefficient one norm of a Hamiltonian, which you can think of as sort of like an energy scale of the problem, plus some logarithmic overhead in the precision as well. And this is kind of nice because I like to think that there's some physical intuition behind it. You don't expect a computer that's built out of the same laws of nature to be able to simulate something faster in time than it naturally occurs. So you expect something linear in T is the best you can kind of do. Okay, so now I want to talk about Lindblad dynamics, which are non-unitary. So, and the reason for this, again, is like in your lab or in nature in general, there's no such thing as a perfectly closed, isolated system. So systems naturally thermalize, they exchange energy with an environment, or you might want to study how an observable will evolve under a thermalization process or something like that. So the Lindblad is also a CPTP, completely positive and trace preserving, and describes the time evolution of some density matrix that's of a system that's coupled to an environment. And it's going to give an accurate description of what's called Markovian dynamics. So in this case, we don't build up correlations with our environment or bath of time. The bath is featureless and memoryless. So when we write down a differential equation, the propagator is not going to depend on previous points in time. There's going to be no memory integral or anything like that. And I will say an important feature of this is that the Lindblad equation is derived as a perturbative expansion, so it's not exact, and it's sort of has error, loosely speaking, in the third order of the coupling between the system and bath. So it's an equation that's derived under weak coupling assumptions. So here it is. It's a differential equation for rho. And this sort of first component here is a typical von Neumann equation for unitary evolution under Hamiltonian. And then we have some dissipative part where these L's are called jump operators, which basically just describe the effects of the bath on our system. They do some energy exchange. And we have these rates as well. And we can also write this nicely with super operator notation with this curly L here. And similarly to the Schrodinger equation, again, it has a propagator that looks like this. which doesn't depend on a history of the bath or anything like that. However, now we're dealing with non-unitary dynamics, which are not trivial to just use our state-of-the-art Hamiltonian simulation algorithms. Another important fact is that this is a quantum channel, one time is positive. And like I said, Hamiltonian evolution is thought of when all these LKs are zero, and we have just our one line equation here. Okay, so now I'm going to talk about or introduce this sort of another framework of writing down open systems called repeated interactions. So this is also another Markovian process. And we think about here as a Hamiltonian that's repeatedly interacting with a discrete part of a larger bath, and then that part is kind of discarded. So again, we don't build up a memory like this either. And we can view this as embedding this non-unitary dynamics in a larger Hilbert space, in the sense that we briefly interact with a subsystem, evolve, and then discard it. So just to give some mathematical context here, we have some Hilbert space that is the free Hamiltonian subscripted by zero with our environment Hilbert space, where the environment is composed of m smaller discrete environment subsystems. And we can write our Hamiltonian, or total Hamiltonian like this, where we have the free evolution. We have some free environment evolution term, as well as the interaction that's strength is modulated by lambda here. So for some short interaction time, we can write down a map that sort of does this process like so. So this is just for a single iteration with one finite element of the bath, where the map itself is only acting on row S. So part of the action of the map is to dilate the system and tensor on part of the environment, do some unitary evolution, and then trace it out or discard the environment subspace. And then, yeah, by iterating this process for some desired simulation time, we can generate the dynamics. Okay, so keeping the map up here, I'll just sort of go through this construction in more detail. So if you think about it physically, our system is kind of moving along a chain. It interacts with part of the environment once, and then the other part just goes off to infinity. Again, it's not building up any entanglement here. But the energy can be exchanged, and the trace out makes the process overall non-unitary. So the action of the map, like I said, stitches on part of the environment. We perform some joint unitary evolution where I'm just writing this H tilde as the total Hamiltonian, and the tilde is going to represent a certain limit we're working in that I'll introduce shortly. And then we trace out and discard the subspace, and then we're left with rho S evolved for a time tau. Physically speaking, this isn't like a super constructed. It's similar to an actual physical system. Maybe it's motivated its first the writing down of this process first is that of a maser. If you think about if we wanted to describe the field of a electromagnetic field in a cavity that's being like repeatedly perturbed by ions, let's say, this is a very natural way of writing it down because you have an atom that comes in, strongly couples briefly, and then just goes off. It doesn't build up any sort of entanglement. So we can write this also with a bit neater notation by introducing some superoperators. So if we have some superoperator like this, that's a commutator. We can, through the Taylor series, define an exponentiated superoperator, which I kind of glossed over on the previous slide. The Lindblad propagator is also an exponentiated superoperator, but it's just defined as repeated applications of its Taylor series. And then with this nicer notation, our map is simply written like this. Okay, so now we have two sort of schemes that are talking about open system dynamics that are Markovian. So the intuition is now that we want to, since one is partially unitary and it seems like it might be more natural to use on a quantum computer, we want to show that one converges to the other so we can simulate Lindblad dynamics with repeated interactions. So there's not much physical intuition for why this works, but if we work in a specific coupling limit where the lambda, just the system bound coupling, goes 1 over the root of the interaction time, we can show that repeated interactions converge to Lindblad dynamics. And the proof of this is not very illuminating. It's just like a exercise in the Taylor series and tracking a lot of terms, so I won't go through that. But I'll state an informal version of the theorem just to get an idea of the scaling. So given some repeated interaction map that we wrote down, so this one is a little bit more involved where now we're going over a multi-composition of all n sort of discrete parts of our path, and then we're iterating them for nu to control the error in time. And now T over nu is serving the purpose of the tau interaction time that we're working with. So the bound we get is like so, where we take the difference between the Lindblad propagator and our map, and we see that it scales like time squared, and time squared over our sort of interaction with our iteration parameter nu, and multiplied by the induced one norm of the Lindblad, which is just sort of like an energy scale, plus some other eigenvalue bounds that are super important for our purposes here. Besides, you get an immediate corollary by this, like, because this is sort of an error term in your simulation or convergence. If you set this equal to epsilon and just rearrange, you now have an upper bound on nu, which you can think of as the number of interactions we need to slowly converge to these Lindblad dynamics. And this sort of gives us a starting point for our quantum simulation algorithm, because we know how many maps we need to implement with nu, and then we know the complexity of implementing those unitary maps. We can come up with an overall simulation scaling. Okay, so now that we showed that repeated interactions converge, which is a unitary process without the trace, we can converge these Lindblad dynamics. And writing it as a quantum circuit now, what you have is you have all your sort of path elements prepared in these registers on the left, and you do all these unitaries between the system at the top and each path element, and then at the end you just trace over, you measure and discard the path. But what's nice is if we want to study some thermalization process, we can efficiently prepare these rows to just be single qubit thermal states, which the complexity of doing so is going to be a lot less than actually implementing U. So on the fly, you can do this with far fewer ancilla qubits, where now you can just prepare, do your evolution, trace out, and just iterate, and you'll slowly end up with an approximation for Lindblad dynamics at the end. So now that we have unitary processes, we can return to the topic at the beginning of the talk and use our state-of-the-art Hamiltonian simulation algorithms to implement these unitaries. Okay, so we should go through this complexity. How am I doing for time?
7 more minutes.
Oh, yeah, okay. So I'll briefly say that then, here these unitaries can be implemented using any sort of Hamiltonian simulation you want. We could use Trotter, like Sophia illustrated in her talk, but the bounds we get out of that aren't super illuminating, and I want to compare it to the complexity I gave at the beginning of the talk, so we're going to use more intricate simulation algorithms. So qubitization of the quantum singular value transformation. We're going to need to construct, just to put in context of what the bounds mean, we're going to construct oracles called prepare and select that provide us with some block encoding of the Hamiltonian, as Sophia also discussed. And now, if you're not familiar with the terminology, by oracles, we just mean that we're calling some sort of function repeatedly or some subroutine that provides us with part of the problem that's necessary. And when we query oracles, we're just meaning we're like calling a function or calling a subroutine repeatedly. So I'll write out the Hamiltonian in some different notation now. So we have this A, which describes the total Hamiltonian for specific discrete part of the environment and a specific interaction. So that's why we have everything subscript by n, because we have n sort of interactions going on here. And this tau on the interaction Hamiltonian is just to remind us that since the coupling went like 1/root tau, there's a factor of root tau absorbed in there. So it's a time dependent operator or it's parameterized by time purposes here. And we're just writing this sum as each ASN is a unitary operator, and there's some coefficient in front of it. So now we have these oracles prepare and select that are one is just like it's just going to encode all of these alphas, the coefficients on some state. And then if we think about some ancilla state all in the zero, like the zero initial state as an like ancillary register, we're just going to prepare this. And then we have another register that's the system might want to act on. So select then acts on this prepared state, and basically just use some control logic to pick out every one of these SNs and apply the corresponding unitary. And if you sort of look at what this does overall, if we apply prepare, then select, and then undo the prepare, this gives us our block encoding. So the purpose of this isn't to explain how quantization and QSPT works, it's quite technical and we don't have enough time for that. But this is just to give an idea of what the query complexity I'm going to introduce, discuss this. When you actually do implement these algorithms, what they do is they perform a series of reflections and rotations about this sort of effective cubitized space to encode the exponential of the evolution that we want. So another informal theorem statement, cubitization or constant value transformation requires QPS queries to these oracles to implement repeated interaction map with upside error. And the boundary gets like this. So the max is just for the worst case part of the environment. So you can just focus on the rest of the terms, I guess. Where alpha naught is the coefficient norm for the total Hamiltonian. We have the bath frequency and then the number of baths we have. And that follows the optimal scaling where we're just linear in time multiplied by some larger alpha. And then we have some slightly different scaling here where our sort of polylogarithmic error term is now multiplied by mu, which was, if we recall, the convergence parameter for how many times we need to iterate to converge to the repeated interaction map in the first place. And then we have some alpha term that scales better or sublinearly in time if we consider mu to be a constant. So if we try and simplify this and work in some recoupling limit where the alpha naught term dominates over the interaction because we're usually working in recoupling in the first place, we get a complexity that looks like this, which again, if you compare it to the one I introduced at the very beginning, it looks optimal except for this just new parameter, which we're converging to in the case for using repeated interactions in the first place. So I'll introduce or talk briefly about some questions I'm still interested in. Nice. So there's a question of which method now, Lindblad or repeated interactions actually capture the molecular physics. So different from many other bounds in the literature, this convergence parameter where we're sort of implementing one map to converge to another. If you recall at the beginning when I introduced the Lindblad equation, it's also not exact. So it's unclear what the role of mu plays in general, because I'm sure we can write down systems or Hamiltonians like the maser I talked about as well, where the repeated interactions actually capture the dynamics more accurately than the Lindblad equation, right? Like if I have some cavity that I'm repeatedly hitting with atoms, I'm not going to try and derive a Lindblad equation for that. I'm getting these repeated interactions. So in order for like, this kind of brings up questions of how you properly proceed when we're considering complexities in open systems, because it's not always clear what the best method is in the first place. And you may be converging to an approximation that's actually worse than just doing your simulation with these sort of CPT maps I talked about. Now, some other general questions. We saw the convergence of t squared in time. I was wondering if there are methods to generate higher order convergences. If it is possible, different techniques will probably be needed because expanding super operators to higher orders in the Taylor series is an absolute mess and very hard to do algebra. Can we actually saturate this lower bound from Hamiltonian simulation? In our case, not have that new parameter there that we had in front of the polylog. And then everything I did was in this big O notation, but when we're actually thinking of how hard these are going to be to implement one day, we want to precisely characterize costs. So numerics is also an important thing to do in this front. And the last question is, are there other CPTP maps that more accurately converge to the blended dynamics on a quantum computer? And yeah, that's everything. Thanks for listening.